Good afternoon, it's Jeremy. It's Tuesday, October the 27th. We're just in lockdown in Toronto here. And instead of talking about COVID-19 taking lives, we're going to talk about saving lives using EPIRB. So right here we have my marine antenna set up on the apartment balcony railing. And it's got an RG58 coax cable going inside. We're going to look at that setup. So it's got about a 1 meter whip on the antenna. There's my ATSC antenna. I put pieces of foam on the ends because it's easy to poke your eye out. So let's go inside here. And here's where the coax comes in. So the coax is coming in here, and it's got a PL259 connector on it. So I've had to adapt it. I'm using the second version of the RTL-SDR with the SMA connector. So basically it's got a PL259 with a female in between, then a PL259 to BNC, and then a female BNC to BNC to SMA adapter. So that's how I've hooked it up to the RTL-SDR. And then I've got a port extender here. So I've got a USB, a flash drive there. That's a connection to the computer. That's my RTL-SDR, and that's the mic and the camera. And then over here right now we're receiving marine weather on the RTL-SDR. So what we're going to do now is I'm going to shift over to the computer, and we're going to go through the blog post and discuss EPIRB. Okay, so now I'm on the computer, and here's the blog post. RTL-SDR for EPIRB. EPIRB stands for Emergency Position Indicating Radio Beacon. Now the idea for this blog post came to me. I was reading a book this summer which I found really interesting, and it's called The Raftsman by Ryan Barnett. Ryan Barnett is a Montreal documentary film producer, and it was a really interesting book. And it's about three Canadians, Henri Baudou, Gaston Vanecker, and Marc Medina, and they went out in 1957. They built a raft and they floated from Nova Scotia all the way to England. And what I found interesting was in the book they had a picture of a device which is called the Gibson Girl, and there's a picture of it there. The Gibson Girl was kind of an emergency survival radio that was developed in World War II, and there's an excellent YouTube video by VK3ASE in Australia, and he goes through the whole operation of the Gibson Girl. But that's what kind of got my interest, and I looked into the sort of the history of EPIRBs, and I got a little table. There's another picture of the Gibson Girl. When I was a kid in the 60s, when I first got my ham license, I couldn't afford a very expensive transceiver, so I bought these BC surplus, I think they were aircraft radios. Absolutely incredible construction. They were really well made. And this is a series of similar radios. The BC 778 was a survival radio, really built rugged, and they probably still work today, and you can see that from the video. But here's kind of a little history of, let's say, survival radios. And then the kind of moving to the ELT, or the emergency locating transmitters, up to EPIRB and GPIRB. So back in the 20s, for instance, at the time of, let's say, or 1910 even, they had spark gap transmitters invented by Marconi. And so in lifeboats, let's say in the Titanic, they would have had let's say a spark gap transmitter, and it worked on the emergency frequency of those days, which would be 500 kilohertz, and you could send Morse with a Morse code key. And you would later on in the 40s, during World War II, they came up with what we just saw there, the Gibson Girl. It also worked on 500 kilohertz, and it had an automatic Morse SOS. It came with 500 kilohertz is a long wavelength, so you needed a long antenna. So basically, you could have a kite flying a wire, or you could have, let's say, a balloon fill it with hydrogen and raise the wire up high. 500 kilohertz would be a long wavelength, so that's half a megahertz, so that's 600 meter wavelength. And so you need at least a tenth of that. So you need a wire that was at least 60 meters long, which is like about 200 feet. That's why you would need a kite or a balloon. So in the 50s then, they came up with the emergency locator transmitter for aircraft. It worked on 121.5 megahertz. After World War II, UHF and VHF became popular because the devices were available. Before that, you can go up high that high in frequency. And it worked on AM, and it had an alarm signal, which was a they call it the siren signal. So it was a tone going from 1600 hertz down to 300 hertz. And then later on, like around 2009 for aviation, they went up to 406 megahertz, although there's still devices with 121.5 megahertz, which is useful for locating things with a radio direction finder. Now the EPIRB came into being when the COSPAS SARSAT satellite system was introduced, and that was in the early 80s. So they're a bunch of LEO satellites that are continually revolving around the Earth. So the way they work is they detect a beacon transmission, and since the satellites are moving, when they're moving towards the beacon, the frequency goes up, and when they're moving away from the beacon, the frequency goes down. This is the Doppler effect. So basically you can get a track and a bearing from one satellite on the device, and if you have a couple of satellites, you can get a triangulation and locate your device. So starting in 1982, they went up to 406 megahertz, and they would have digital information. They would call it a hex code, and it was embedded into the EPIRB, and that would be able to, you could look that up and see what kind of registration information it had. It would be sent to the appropriate country to say that that particular person was lost. Later on, when the GPS satellite system came into being, they came up with the same idea, but they had a longer packet of information, and then in there they would put in the GPS coordinates. They call that the GPIRB, or the advanced EPIRB. They would also have built into the device a 125.5 megahertz location transmitter with low power. So once they're looking for the particular individual, the LEO satellites of SARSAT would get a triangulation, and then they move in, let's say with a plane, looking for the guy, and then they could use the 121.5 megahertz at a very low power to home in accurately. So what I've done here is I've simulated actually the siren signal in Psychos. So I've got a sawtooth generator, and what I'm going to do is I'm going to use that to drive a VCO. This is a variable controlled oscillator. So the higher the voltage, the higher the frequency. So we can actually see that. Let's get the model here. So there's the model, and let's run it. So there's the sawtooth. Now the frequency of the siren signal is 2 to 4 cycles per second. So that's the output, and we can blow that up and look at it. So if I just look at here, so there we are, there's 1600 hertz and there's 300 hertz. We can actually also listen to this. So there's the wave file. So that's what it sounds like. On the ELT devices, the siren signal is downward from 1600 to 300, and on the PLB, personal locator beacons, which are popular now, the siren signal goes up, so it goes up from 300 to 1600 hertz. So the next thing I do in my blog post here is I look at the, this is a 406 megahertz system, the newer system, the EPIRB. And this is taken from the COSPAS technical specification T.001. It's quite current. It's available online in the references, and it was dated 2018. So basically then you've got a short message and a long message. The short message is the one that doesn't contain the GPS coordinates, and the long message has the GPS coordinates in it. So basically you have a burst of about, let's say, half a second of digital information on 406 megahertz. And then you wait randomly between 27 and 30 seconds. It's random. So it's kind of like a random access type of thing, so you don't interfere if there's several people transmitting. On average, it's about 28.5 seconds. Then you get another burst of information. Within the packet, that's the short packet, and that's the long packet. So you start off with 160 milliseconds of pure carrier. So basically the 406, actually it's 406.025. It goes out with no shift. And then the next thing you have is you have data or bit synchronization. You've got 15 ones, And then you've got a frame synchronization pattern. There it is there. And then this bit tells you whether you have a short message or a long message. If it's set to 1, it's a long message. And within here, you've got all the registration information and the GPS coordinates. So what I did is I built a simulation in Psycho. So I built all these bits in there. And for this section here, I've just put in a random bit sequence because it's going to be random data. It also has BCH, Bose-Truduri-Hockenheim codes, a 3 error correcting code built in there to correct any mistakes. So there's a block showing you how the various information is encoded in there. Everything is in this spec. It's very, very detailed. There's the modulation. The modulation is Manchester encoding. So if you have a 1, you go from a 1 to a -1. Now, the modulation is phase shifted. So a 1 is plus 1.1 radian shifted up, and then minus is minus 1.1 shifted down. And so there's the Manchester encoding. The bit rate is 400 bits per second. So there's the Psychos model that I came up with. So I create the packet in the editor, which is much easier to do. That's what I do with all my modems. I create it in the editor. Then I create a structure and I read it in. So basically what happens here is I've got a 406 megahertz generator at plus 1.1 radians, and then I've got a 406 megahertz generator here at minus 1.1 radians, and I've got one at 0 radians, and this is 160 milliseconds of carrier with no modulation on it. And I read it in here. Now I've added 2 here. I'm using a multi-port switch. So if I see a 3, then I get input 3. If I see a 2, I get the middle input, and if I see a 1, I get this input, and then I see my output. So we can have a look here. This is the editor, and what I've done there is I've built my message. So there's my 15 ones for the bit sync. There's my frame sync. There's my 1 saying I've got a long message. So I create my message there. This is for my Manchester encoding. And then I add the 64 bits of carrier, and then I create my structure. I can look at this. There's a plot of the data. So there's my 160 milliseconds. Now 0 read into the Psychos model will give me the 0 shift. So there's no shift in the carrier. And there are my 15 ones, and there's random data there, and there's my frame sync and the 1 bit for the long message. So that's my message. And we can look at, let's open this up and run it and see what happens. There we are there. Okay, so let's run the simulation. So there's a simulation. So there's my structure read in from the console. There's my 0 phase. That's what I'm going to have here. I've got 160 milliseconds of carrier with no shift. There's my, I think it's the plus 1.1, and that's the minus 1.1, and that's my output. If I blow it up in here, you'll see all the phase hits for the data. So every time you've got this thing shifting up and down, you've got phase hits in there. Now if I look at the spectrum, there's my spectrum. Now what am I going to see? Well, I'm going to see, now for simplicity purposes, I've instead of putting this at 406 megahertz, I put it at 400 hertz, or sorry, 4000 hertz, just so I could see the sidebands. So what I'm seeing here is I'm seeing the 15 ones, I'm seeing 400 hertz, which is the baud rate. I'm seeing those harmonics in there all over the place. And I'm seeing a data null. Now, the Manchester requires twice the bandwidth of NRZ, so if my bit rate is 400 bits per second, I need 800 hertz for the first 0. So those are the nulls, plus or minus 800 hertz either side of the carrier from the Manchester. Okay, so let's go back to our post here. Okay, so that's the simulation with the EPIRB. And now let's look at RTL-SDR reception. So let's go into SDR sharp. So what I'm doing here is I'm just checking out the marine band. So that's 162.4 megahertz. That's Toronto weather. Okay. Now I've got it set up down here for ELT emergency. So I'm going to go to 121.5 AM and see if I can listen, hear anything. So there's 121.5, and I don't hear anything. So clearly there's no emergency going on at that frequency. Thank God. And then let's look at the EPIRB frequency. So there's the EPIRB frequency, 406.025, and I don't hear anything on there as well. Now, the only way you're going to pick up ELT or EPIRB frequencies using the RTL-SDR locally is if obviously the emergency beacon is within your VHF range or your ELT range. Now another thing we can do, let's just mute this for a minute. The other thing we can do is there is a program called multi-PSK, which is a very, very interesting and detailed decoding program. And in multi-PSK, there is a whole section on EPIRB, and you can decode EPIRB transmissions using multi-PSK, and you can also control the RTL-SDR. Now, what they mention in here in the help section is that the satellites, the LEO satellites, retransmit the received messages. So even though you might not be able to hear a local beacon in distress, you can monitor the satellites to see what they're picking up. So what I'd like to do in a later blog post and video is we'll look at using the RTL-SDR with multi-PSK, and instead of looking locally for a beacon, we'll look, see if we can pick them up off the satellites.